Okay, so the goal of this video is to look at some trig properties, things that probably you looked at last year, and I just wanted to remind you, review, and put some, and maybe put a few more things together in this idea of analytic trig, like just studying trig as functions. And so there's a couple of practice questions or some application problems. And so the first one says, suppose you have 2 comma -4 on the terminal side of theta in standard position. So again, making sure we know standard position. Remember, standard position always starts in the positive x-axis. So I'm going to start here and always go in a counterclockwise direction. So 2 -4, 1, 2, 3, 4 is actually down here. So this is the terminal side of the angle. The initial side of the angle is here. Maybe I should pick another color just so I can distinguish that. Here's your initial side. Here's your terminal side, and it must go in a counterclockwise direction. So really, it's that large angle there. But then what I can do is just draw that reference triangle right to the x-axis. And so I've got a little right triangle that if I enlarge that, I went over 2 and I went down 4. And so even though the angle that I'm looking at is greater than 270 degrees, really it's this guy right there is a reference triangle or reference angle that I'm going to use. And I can use the Pythagorean theorem to simplify this. 2 squared plus 4 squared. So 4 plus 16 is root 20. So I know my hypotenuse is root 20, which simplifies to 2 root 5. And now it says, find the 6 trig values. So once I've set that triangle up, I can just do sine of theta. Again, this is our theta here, so it would be -4 over 2 root 5, which we could reduce to -2 over root 5, and then re-rationalize that -2 root 5 over 5. Cosine of theta. So cosine of theta is adjacent over hypotenuse. So it would be 2 over 2 root 5, and it'll be positive. The 2's cancel, so we get 1 over root 5, or we can multiply by the denominator and get root 5 over 5. Now, tangent would be opposite over adjacent. So that would be -4 to 2, which is -2. And then we do the reciprocal function. So cosecant of theta, which would be 2 root 5 over -4. Hypotenuse over opposite, and that could reduce to root 5 over -2. Excuse me. Secant of theta, which is equal to hypotenuse over adjacent. So 2 root 5 over 2, which is root 5. And then our final one for that problem is cotangent of theta, which is the adjacent over the opposite. So that would be -1/2. Okay. So again, just I guess maybe vocabulary there, making sure, standard position, terminal side is the ending, or the initial side would be the beginning. Okay, so 54 degrees now for the next example in standard form. So again, thinking about what does standard form look like? It starts on the positive x-axis, and you open in a counterclockwise direction. So there's 54 degrees. Now, coterminal means that you start and end in the same spot. So I'd want to make sure I still start here, and I want to be coterminal with the ending ray of the 54-degree angle. So one way to do that is just to go around more than once. So, and I can draw that kind of little spiral in there and say, okay, there's the ending. So that would be 360 plus the 54 degrees. Right? So then one coterminal angle would be 414 degrees. Now you could go another 360 degrees around there, right? So then you add plus another 360. So you could say 414 plus another 360, which would be what, 774, I think, if I did my math right. If I didn't, I apologize. But now you could also go backwards, right? So you could start, I'll go, I guess, in blue here. So you could start at the same spot and go in this direction. And that's a negative value, so that would be -306 degrees. And, you can continue to go in that negative direction. Okay, next one, it says cotangent is 5, and it says the cosine is negative. What is the value of cosecant? So if I think about cotangent being 5, it's a positive ratio, and remember it's adjacent to opposite, so it's a 5. I can think of 5 to 1. Well, one position I could put that is in the first quadrant. I can make 5 to 1, 5 to 1 ratio, and that could be one place where my theta could be drawn. But the thing is that cosine is not negative there. Cosine is negative in quadrants 2 and 3 over here, because that's where x is negative and cosine depends on x. So I could draw it in the second quadrant, but then my cotangent wouldn't be positive. So the quadrant that I need to draw this in has to be the third quadrant. And so drawing it down here in quadrant 3, making that -5 to -1 as a cotangent ratio, it becomes positive. And then that becomes the square root of 26 using the Pythagorean theorem. So now it says find the value of cosecant. So it's hypotenuse divided by the opposite. So that's -√26. Okay. Now, similar case, it says sine is 1/7. Find cosine. Now, sine is 1/7. It only gives us one parameter. It just says the sine ratio is 1/7. So like 1 to 7 ratio. Right? So there's one way to represent that. But the thing is, I could also draw my triangle over here, and that's also a 1 to 7 ratio. So since I only have one constraint, not two, like the example 3, I had 2 different things I had to keep track of. Here, just one. So if I think about completing the Pythagorean theorem, right? So I don't know what this missing side is. Call it x, right? So like x squared plus 1 squared equals 7 squared. So I know that that's 49 minus 1 is 48. So x squared equals 48. So x is equal to plus or minus, introducing the square root, the square root of 48 has a perfect square of 16. So that's 4√3. Well, I love this idea of plus or minus because one side would be a positive 4√3, but here's the negative root 4√3. And both of those triangles have a sine ratio that's positive. So when it asks for cosine, if you're in the first quadrant, your cosine value is 4√3/7. All right, it's the adjacent piece over the hypotenuse. If you're in the second quadrant, you are -4√3/7. Or you can combine them and say it's plus or minus 4√3/7. And again, I want to make sure that that makes sense in terms of, why did we get 2 answers? Because we only had one constraint. Just the sine was positive 1/7. In the previous one, we actually had 2 constraints. Cotangent and cosine had to follow. We had to follow that. And this right, Pythagorean theorem, actually, that's going to lead us into the Pythagorean identities, which come a little bit later in the notes, but I'm going to go ahead and throw that in right here, because I know that you guys talked about this last year, or at least you should have looked at that and maybe forgotten. That's okay. But there are 3 Pythagorean identities that we need to know in this class, based on trig, and it all boils down to a right triangle, and we're going to go back into the unit circle. So my hypotenuse will be 1. So there's the x, there's the y, there's the 1. Here's my random theta, arbitrary. And again, I'm in the unit circle, so that my radius is 1. And just based here, I know that x squared plus y squared equals 1 from just the Pythagorean theorem. But if I think about a trig ratio, let's say the sine of theta is equal to y over 1, so that's just y, and the cosine of theta is equal to x over 1, which is x, I can replace x squared with cosine squared of theta, and I can replace y squared with sine squared of theta equals 1. And so that's the Pythagorean identity you probably saw last year. And I know we talked about this on an earlier video, that if you see cosine squared of theta, what does that mean? It means it takes cosine theta times cosine of theta. right? Cosine squared, cosine times cosine. Okay. And same thing, sine squared is sine times sine. So that's our first Pythagorean identity. Cosine squared plus sine squared equals 1, or using just the commutative property of addition, sine squared theta plus cosine squared theta equals 1. Now, I'm going to derive the other two. So the first one I'm going to get is I'm going to divide every term by sine squared. Divide each of those terms by sine squared. And so that means that sine squared divided by sine squared, which I know can simplify, plus cosine squared divided by sine squared equals 1 divided by sine squared. And so if we simplify this, well, sine squared divided by sine squared is 1. The reciprocal of sine squared over here is cosecant squared. And if we're worried about like cosine squared over sine squared and we don't quite remember that, well, that's cosine squared, that's the x term, the x component divided by the y. So in a triangle, if you have the x divided by the y, you're cotangent. So this is cotangent squared. So that's our second one we have to know. And then, if I divide it by sine squared in that direction, logic might tell me that I could divide by cosine squared to derive the third one. And so I'm going to divide each of those terms by cosine. Here's the work. So sine squared theta divided by cosine squared theta plus cosine squared theta divided by cosine squared theta equals 1 divided by cosine squared theta. And again, looking and simplifying, I know that cosine squared divided by cosine squared is 1. I know the reciprocal of cosine is secant, so this would be secant squared of theta. And then similarly, if you're not familiar with what's sine over cosine, it's the y over the x. So which trig ratio is the y divided by the x? Oh, that's tangent. So that's tangent squared. So you need to know the 3 Pythagorean identities. And the one that most students remember, I guess, most often, the easiest one to them is this one, right? Sine squared plus cosine squared equals 1. But the other two are equally important, and you'll need to know those, that 1 plus cotangent squared equals cosecant squared, and tangent squared plus 1 equals secant squared. Now, I often talk about like how my feet are in 2 different classes, right? Honors Pre-Calc and Calc BC. But, in general, in math, as you move on, these relationships, these pairings, come up quite a bit. Like in calculus, sines and cosines will pair together, and cotangent and cosecant will pair together, and tangent and secant will pair together. So, again, some of that should look familiar. Some of that might be an extension from what you learned last year. But what we'll do is then we'll look at some more examples and continue to build this, this base for our trig functions.